So I'm Erik Bjorge.
And I'm Maggie Jauregui.
And we're here to talk a little bit about attacking and defending the platform. So this actually plays well off of the last presentation, because we're going to be covering a lot of the same things. So first of all, legal notice. If you were here yesterday, Brent did a great job with this. No system is secure. Moving on. So we've got basically three types of attacks we're going to look at today. We're going to look at the variable store, because this is a favorite place to attack, and there continues to be a number of issues with this. We're going to look at SMM, because once again, another place that everyone likes to attack, and you get an amazing level of privilege. And last but not least, we're going to look at using a limited physical attack to provide bonus material to your firmware to allow the attacker to do neat and cool things.
All right, let's start at the lowest level of privilege, an unprivileged software attack. What could a Ring 3 level access attacker do to gain persistence on a system? So, as we've mentioned before, variables may be an interesting place to start because of the sensitive nature of the data that may be contained in them, such as configurations for different security features, hardware protections. Some of this data is just really, really necessary for the platform to be able to boot. And also, variables provide an interesting channel as a covert channel in which you could potentially, from Ring 3, exfiltrate some interesting data to store there in a way that isn't easily detectable, but an attacker could come back later and the data would persist there in plain text. All right, we've determined that variables are important and must be protected. How can we do this? So there are a few mitigations that we can implement, but the main concept is the same. Limit access, least privilege access. So speaking of limited physical access attacks, we've been walking around and people have been kind enough to allow us to plug things into their systems. And we've observed that the attributes for variables, for the most part, tend to have both runtime and boot service access on pretty much every variable in the system. Does every variable actually need runtime access? This is an exercise we understand to be tedious, but we also stress that it's important to sit down and do. Limit the variables that actually need that runtime access, and every other variable only gets boot services. Within the ones that actually need the runtime access, do you actually need read access to them or write access to them? So for the ones that you only need read access to, we can lock and make sure that you cannot modify them after the end of Dixie event. For the ones that you actually need to write, there's a couple of different things we can do, and I'll go back here because I missed a couple. There's authenticated variables that are either protected by a monotonic count or a timestamp from replay attacks. And there are also things like varchecklib and TianoCore that we can use to sanity check the data that's written to these variables so that we make sure that whatever's attempted to be written there makes sense for that variable. And even though we've spoken about nearly 5 different mitigations to protect variables, these are not enough. An attack that we could do is to create a new variable, an evil nvar, that we could exfiltrate data from the OS and store a certificate or a private key for later use or harvest.
So the reason we would do that is because most of the time, your security software is not going to be checking for, interesting pieces of data like private keys to be floating, into the variable store. They'll look for them on the network. They'll look for them throughout the rest of your software stack. But they're not going to necessarily check your flash part. However, if I can take a signed, shimmed version of Ubuntu or whatever, walk up to your system after this has been stored, I have variable access from there, and it was, even with secure boot on, I was able to boot it, assuming you allowed me to, boot from a USB drive. So this is one of the things where we need to start looking at limiting what people can, do that's unexpected. So we need to go through and potentially modify the var checker lib so that you have a mode where you don't allow unexpected variables to be written. This doesn't work in all systems, but if you have a closed enough system where you're not worried about, let's say, third-party option ROMs writing variables, you could limit the access to the NV store. So let's move right along to our favorite, which is, of course, the SMI confused deputy. So we all know what SMIs are. We all know what SMM is. And we all know what the confused deputy does. It's just a way for me to massage the input values to an SMI to make it do something exciting. It's either write over data, cause an overflow, who knows what. So we've also gone through all of the mitigations that we have currently. We limit the memory range that we have mapped so that you don't have access outside of SMRAM and the allowed resources. We go ahead and now we need to start looking through and reducing what we put into SMRAM. Do we really need to do things in SMRAM? There are a lot of things that we do because it's easy. There are a lot of things that it just has to be done that way because of certain security requirements. The thing that we need to do is we need to remove the things that are just easy and may be able to be done in an OS present driver or through some other means. And even with all of the additional protections that we've added, and theoretically with the reduction of code in SMRAM, we still need to go through and we need to use tools to fuzz and test our SMI handlers to make sure that we don't have any bad behaving tools or APIs. So one of the things that you can do is you can use chipsec to do this or any other fuzzer you'd like to write. So now we can move on to the limited physical attack. So this one is an example by Crash. He provided a modified SMI handler. He took an existing SMM driver, took it out of the flash, modified it, reinserted it back into the flash. And
gee, Eric, do you really need to go through all that trouble to do that?
Not really, actually. This was actually a little bit too much work. You could have just added it to the existing FV, but this is how he implemented it. But the cool thing is that he implemented a full API for reading and writing memory. So he created a very useful tool in SMRAM. The problem is you probably didn't expect it to be there. Along with this, you have hacking teams, commercial rootkit. Everyone likes to talk about this, bad BIOS. This was another case where people used a flash programmer to insert, or a vulnerability to insert extra UEFI modules. These allowed the malware to remain persistent across OS reinstalls. The nice thing is an NTFS driver will allow you to put your malware back on right after you do a new install of your OS. So where are we targeting? As in the previous presentation, we were talking about really putting drivers into PEI and Dixie. This allows you to either gain access really early in post or to allow you to have access like in Dixie. You can write SMM drivers and load them and have runtime access, which is fabulous. And as I alluded to, you don't always have to use a spy programmer if you have a very broken BIOS and you do not protect your flash. I can have a runtime access from the OS to add my fabulous payloads to your firmware.
All right, is there anything we can do to protect against physical look at the map of the different attack vectors, and there's software, there's physical, the line in the sand used to be right in the middle, where if we had any kind of physical access, game over. I do not protect against that. And times are changing, so there are things, detection and mitigation mechanisms against things. Protection and detection. One of the things you really want to do is you want to make sure that they actually need physical access. So make sure that no one can write to your BIOS. Enable BIOS write protect. This is non-negotiable, no excuses. There's a chipsec module, go check it, set it. This way you ensure that software cannot modify or add any firmware volumes. Make evil Erik work for it. Aside from having hardware root of trust, for example, we also have detection mechanisms like whitelisting. So with chipsec, you can enumerate your firmware volumes along with hashes for each one of them that you can then compare against a good known whitelist to make sure that the firmware that you're running is the firmware you're expecting to be running. And this is one of our calls to action where having golden whitelists from vendors would be interesting so that any user in the world at any time could check and make sure that what they're running is what the vendor intended for them to be running. And we have a blog post on whitelists and how to use them. Whenever you get the material for the talk, you can click on that last link. We have a couple of snapshots of whitelists. This one specifically generates the whitelist. There's the instruction. And then you would check against a good known one. This screenshot specifically are the 3 firmware volumes that were for hacking team's bad BIOS. So you can see the warning there. We found 3 UEFI executables not in the list. All right, and we're very aware of the target audience of this talk. We know you know these things. These are ABCs and very basics, and we also know that you understand that this is not an exhaustive list of every attack and every attack vector. There are a variety of forensic artifacts that exist so that we can, as sort of thermometers to tell whether or not something bad has happened. We have ACPI table sets and BIOS, we have TPM PCRs, so we know you're aware of them. It's just a friendly reminder to cover your basics. All right, that's it. Erik and I are battling for who gets to do the outro.
So anyway, conclusion. We have a set of assets that we described in our threat model previously. We have a list of attackers, and we have the goal of protecting, detecting, and recovering. So to do that, we would like to ask that everyone goes out and looks at your UEFI variables. Only give them the access that they need. If you don't need runtime access, get rid of the runtime flag. If you do need access to the variables at runtime, go ahead and put them in, create a var checker lib for it so that you can actually go through and validate that the settings that you are getting being added are not insane. Make sure that you lock the variables that you do want runtime visibility to, but you really want them to be read-only. Do the right thing and try to take your security sensitive information and double check that. The other thing is SMRAM. Go ahead, reduce your footprint. Take the things out of there that don't belong. I know it's crack, it's really easy, you have all access to everything, but do you really need that access to get the job done? If you don't, try to find another way. And then when you get done cleaning out SMRAM, go through and everything that remains, make sure you do input checking. Make sure you do fuzzing. Go through and double check everything because that's where people are going to try to break you. And the third thing is go ahead and try to make your firmware more, trying to make it more easier for you to detect whether there's been a modification to it. So enable a root of trust. Go ahead and check your PCRs. Make sure you measure everything. Do all of the things so that you can easily detect that someone has done something evil to your firmware. And then also, on top of that, make sure that you have locked your flash parts, your storage devices. So as you can see, I lost, and I was not very good at that, but we'll just move on. Anyway, so thank you. If you have any questions.
Actually, this isn't, I tried to give ample time. This isn't so much a question as it is a comment, since you hammered on the SMM protections. A couple of things that have happened in Tiana Core over the last year are the SMI handler profiler, which is actually really useful if people haven't taken a look at it. It can be combined with an auditing tool that will dump all of the handlers that were registered in SMM, so that on any given build you can say, hey, did I register something I wasn't expecting for? It's great for defining that audit surface so that you can go back and check each one of those and see how well it works.
And you can check to make sure if something's made a reappearance.
Exactly, yeah. It's fantastic for CI processes to have like a golden copy of what we expect to be there, and then you can throw up a big bang if anything shows up because you took a code integration or was there a regression. It just gives you that reassurance that I haven't changed my attack surface at all. And another thing that's happened over the last year is paging protections have become really big in SMM. And not to toot our own horn, but our fearless leader is out shopping around the auditing tool that we just published to our open source and have been working with Intel on refining. So if you'd like to take a look at that, let me know. I'll give you a card and tell you where to go.
Absolutely.
GitHub. It prints pretty pictures that show you exactly which memory ranges are exposed to SMM based on your current page table settings.
Right, cool, thank you.
Do you have a recommended root of trust?
So, a hardware root of trust would be good. Good answer. However, yes, you can implement that in many ways. And that's all I'm saying.
Are you doing anything about with whitelisting? Whitelisting other pieces of firmware on the main board other than?
So right now, all we do is we tear apart the either a capsule or your flash device. So that's all we're looking at. So UEFI images at this point. No, we haven't torn apart the ish or anything like that, but that is a possibility. So it is chipsec. It's an open source tool. So if you'd like to make a contribution,
sure. If I could release all the orange cover related things that would be tied to it.
I have my own windmills to tilt at.
Okay.
I do have a question. I don't know if you know this guy over here.
Eric, really?
Eric, I hear that SMM is crack, and I was wondering how long you've been in rehab.
Actually, it's been only like 6 months. No, it's maybe 6 weeks since I've written my last evil SMM handler. All right, thank you.